All right, welcome back, everybody. So I'm actually literally like 15 minutes out of teaching you guys. So I was like, why not just make this video right now? I'm like in the calculus mode. So I'm just going to go ahead and just make this video on my board. So I'm teaching to an empty classroom. I'm teaching without my mask on. I feel like I'm such a rebel right now, but there's nobody else in the room, so I feel safe. All right. So we're picking up here. And now those of you who print out the notes, I am going to kind of skip around a little bit. I am not going to do example 3, so you don't have to worry about that if you already done that. If you already printed them out, you can just kind of throw that away. And now I'm going to jump to example 6. And I'm going to jump to example 6 because I want to do example 6 using the property that I kind of showed you. Now it says use the properties. We're going to learn some properties of integrals, but don't use those in this. I want you to use the property of the integral from a to b of fx dx is equal to fx from b to a. Yeah, I want you to use that. Okay, so that's what we're going to do here. Because now the reason I'm doing this is because can we possibly take the antiderivative? And the answer to that is yes, we can, because it's just a polynomial. So therefore, I can take, I know that this is going to be, well, I'm going to rewrite that 3x squared plus 4. I don't know why, I just don't like it like that. So that's f of x. So therefore, big F of x is going to be equal to 3x to the third over 3 plus 4x. And I would write plus a constant, but I don't have to worry about that in this case. I don't have to worry about that. So that means that once I take it from a to b, from 0 to 1, I'm going to find the difference between those two. Okay, so I'm going to do top minus bottom, and honestly, I can just do this, right? Cancel those two. So that's big F of x. So plug in 1, I get 1 plus 4. Plug in 0, I get minus 0. I end up just getting 5. See how easy that is? You know, maybe at some point you should look in your book and see how long the answer to example 6 is. And it's like ridiculously long. So feel really happy about how many steps you're saving yourself right at that moment right there. And how easy it is. And that's what we'll be looking at in section 5.3 when we look at, I'm sorry. Yeah, section 5.3, I believe it's called the fundamental theorem of calculus. All right, so next thing we're going to talk about is this midpoint rule. Now, we have used midpoints to calculate the sums of these rectangles, right? We've talked about using right endpoints, we've talked about using left endpoints, but now we're going to talk about using midpoints. Now, the midpoint rule basically says that we ought to choose the sample point, maybe to be the right endpoint or the left endpoint, but if the purpose of finding an approximation of an integral, it's usually better to choose the midpoint of the interval, right? The problem with choosing a midpoint is that we don't know whether it's an over approximation or under approximation, but it's a good approximation. Any Riemann sum is an approximation of an integral, but if we use midpoints to get the following approximation. So here's what I'm going to do here. I'm going to use midpoints to get a really good approximation of this. Now, all of these things we've done before. Okay, the only difference is now we're using x bar here. Okay, instead of using xi, we're using x bar I, which basically means that I'm going to be using the midpoint. I don't necessarily love the way they write it here. I'm actually going to say, let me flip to my page. I would more likely say find the first term and then make your other subsequent terms based off of your first term. Okay, and to find your first term, you're basically going to find the interval between your very starting value and then your first term, right? Xi minus 1 and then xi. So your starting value, your a value, and then xi. And then you're finding the midpoint of that. That's a better way to write it, in my opinion. Okay, let me show you what I mean here within an example. Use the midpoint rule with n equals 5 to approximate this. See, I'm not, this is like saying I want to use midpoints instead of left endpoints or right endpoints to evaluate 1 over x, our good friend 1 over x, we've done that plenty of times, dx. Okay, that's what we're going to do here. All right, so that means that f of x is 1 over x. Delta x is 2 minus 1 over 5, right? because n is 5 right here. So it's 1 over 5 or just 0.2. I'm going to use the decimal value here, 0.2. Now, what is that telling me about my first interval? My first interval is going from 1 to 1.2, right? That's the first rectangle that I'm going to use. So what's the midpoint of that? Well, that means it's going to be 1.1. That's x1. All right, and I'm going to choose 5 of them because I want 5 strips of these things. Now, I'm using my midpoints, though. I know I want my delta x to be 0.2, but I'm using midpoints. That means my next midpoint has to be 0.2 units away, or 1.3. My next midpoint would be 1.5, then 1.7, then 1.9. Now, how am I getting those? I'm just taking these delta x's and just keep adding them on. So really, if you wanted xi other than 1, you would just be taking your initial value, 1.1 plus delta xi, right? So that's like, we'll give you 2, then 3, then 4, then 5. You kind of have to reason it through for your first one, and then just take that 1.1, and then just keep adding on iterations of delta x. Okay. Now, so that means that the sum is going to be 0.2 times, right, the delta x times all of the little strips, the y values of all of those little strips. So it's going to take f of 1.1 plus f of 1.3 plus f of, and I'm going to run out of room again. I'm going to have to do this. F of 1.5, come on now, plus f of 1.7. Oh, one more, plus f of 1.9. 5 strips, right? 1, 2, 3, 4, 5. Yep, count them up. Okay, so that means it's really, now you don't have to go through this process every time. Like if you're really good at this and saying like, I know I don't have to write it in as f of that thing, I can just plug it in, then do that. I'm okay with that. But I'm just kind of reinforcing what's happening here. All right, now, when I add all those together and then multiply everything by 0.2, I do that in my calculator, I get approximately 0.6919. Right, so that's going from 1 to 2 of 1 over x dx. Okay, that's the integral from 1 to 2, 1 over x dx. Now, what's interesting to point out here is that I'm using the midpoint rule here, right? That's the approximation. Could we possibly find out the actual amount? Yes, because I've taught you the shortcuts. So I'm going to find the integral from 1 over 2 of 1 over x dx. Well, isn't that, like, think about this. F of x is equal to 1 over x. What is capital F then? Oh, isn't that ln of x? The absolute value of ln of x, right? So that means that is equal to ln of x from 2 to 1, right? I don't have to worry about the absolute value because these are what I'm plugging in is full positive. So this is really just ln of 2 minus ln of 1. Ln of 2 minus, oops, sorry, in parentheses, minus ln of 1. How close did we really get? See, this is the actual answer, right? That's the actual answer here. How close did we get using midpoint approximation? I mean, pretty darn close. I feel really good about how closely our midpoint approximation, only using n equals 5, you know, like we could say n equals like 100 and get an even better approximation, but we only use n equals 5. So I don't know, I'd say that's pretty good. In my opinion, it's pretty good. All right. So that's a midpoint rule, basically finding midpoints to use as those values. Again, something that we've already talked about, something we've already used, but now just using it in terms of the integral notation. Okay. And I think that kind of talks about it a little bit here too. But we don't even need to worry about that. When we defined the definite integral, we implicitly used, what do I want to get here? Just trying to like speed things along for you here. These properties, those are important properties here. Okay. I would jot these down for yourself. You know, they tie right hand in hand with the summation properties. They go very, very closely with the summation properties that we've already talked about in this lesson. If you've got a constant as your function, then all you need to do is take the constant times the difference, right? The constant times the difference. If you've got the integral of two functions added together, the sum, you can find the integral of the sums. Or sorry, excuse me, the integral of the sums is the sum of the integrals. If you've got a constant times the function, you can bring that constant out front of the integral because it's not dependent on that integral. It's not dependent on x, so it's not going to change. If you've got a difference, then you can find the difference of the integrals. The integral of the differences is the difference of the integrals. Okay, so those are all those properties here. Another I wanted to illustrate. We're not going to do this last part of this slide here. I just kind of want to show you this top part here. Property 1 states that the integral of a constant is the constant times the length of the interval. You know, we can almost think about that in terms of our, you know, what I've already taught you, kind of like the shortcut that I taught you. But it's interesting to point out in terms of the graph, if you've got y equals c, just a horizontal line, and you want to find the area underneath that curve, well, isn't that just the constant? The constant is just the y value, there is c, times the distance from A to B, right? What is that? The length of that is B minus A. So the area is B minus A times C. Just showing you a visual representation of the integral there. Now, this last property is extremely important. Make sure you jot this down, okay? Now, take a look here. I've got going from A to C. Notice the notation there. A to C plus C to B. What's changing is, okay, so if I've got the same function, as long as that's the same function, fx dx, what I can do is chain these things together. If I go from A to C, then C to B, I can say the sum of that is A to B, right? As long as these two things link together, as long as those two numbers fit together. Like, for example, if I've got the integral from 1 to 2, and then the integral from 2 to 3, that's the integral from 1 to 3, right? I don't even know what types of, you know, okay, let's write it as fx dx, right? Just as long as that's the same, okay? Now, that means, like, think about it logically. If you've got a graph here, and, you know, it's going like this or something, here's 1, here's 2, here's 3, obviously the area here plus the area here is going to equal the area total, right? That's what we're saying here. The area from 1 to 2 plus the area from 2 to 3 is the area from 1 to 3. That just makes sense in our heads there. All right, so if it is known that the integral from 0 to 10 is 17, and the integral from 0 to 8 is 12, find the integral from just 8 to 10. Now look at what I have here. Notice the notation. The only thing that's different is here, here, and there. Okay, so if I want to figure out what the area from 8 to 10 is, notice that I can take my 0 to 10, and that's equal to the sum of 0 to 8 plus 8 to 10. Okay, 0 to 8, and then 8 to 10. So that means that this is 17, this is 12, and this is the unknown. So I subtract over the 12, I get 5. Okay, you can use those algebraic properties like that. Pretty neat, pretty fancy, right? Did I want to say anything else? Oh, I missed that property. Okay, I kind of skipped past it and I should have gone back to it. I'm sorry. This is kind of important as well. Okay, this is kind of important as well. Notice that what we can do here is if these are ever like misordered, like if I wanted the integral from 2 to 1 of fx dx, that is equivalent to the negative integral from 1 to 2 fx dx. I don't know why I write them on completely different sides of that box, but those are equivalent statements, okay? If these numbers were ever switched around, you could You could take the lower and the higher and then subtract the two, and maybe you could chain something together. Or not subtract the two, excuse me, put a negative out front, and maybe we could simplify it down based on that. Okay, one of the last properties here is a comparison property, and mainly this here. You'll see in the homework it says use property number 8 for this. Okay, use property number 8. This is property number 8. Okay, what we can say here is that if you can plug in your b minus a times m, and there's some m value that once you plug in your x, if it's smaller and bigger, it's somewhere in between, kind of like squeezed in there, for all a in between, you know, for all x is in between a and b, then what you can do is multiply that number times the interval, and multiply that number times the interval, and it's gotta be between it and there, okay? Here's what I mean by that. Take a look at this property here, or this problem here. Now notice that I would not even be possibly be able to use, I would not be even possible to use to try to use that you know, that trick that I taught you. Because how are you going to evaluate the antiderivative of e to the negative x, or e to the negative x squared? It's like some sort of chain rule-y type thing. We will eventually do that, but this is one of those that's like, okay, maybe there's some way to estimate it. And that's the key word there, going to estimate it. Okay, now to do so, what we're going to find is that we're going to plug in we're going to plug in both endpoints, 0 and 1. And we're going to see what we're going to get. Well, e to the 0, 0 squared would be 0, and negative 0 is just 0. So e to the 0 is just 1. All right, and now we can say, well, if this is the case, well, negative 1, notice that the negative is not squared, so this is like e to the negative 1, or 1 over e. So let's figure out what that is. E to the negative 1. I don't know why I use parentheses. Screwed me up. 0.3679. Okay, do you notice how this is bigger and this is smaller? Okay, so what I can say here is that if I know that e to the negative, if I know that f of 1, if I can plug that in, and I know this 0.3679 is smaller than that, than plugging in 0, what I can say that this is a true statement, right? And I know that because this is continuous. You know, I know that there's not going to be any gaps or breaks, and I know it's going to keep increasing and keep decreasing. It's not going to basically change directions, okay? It's going to change. It's not going to change directions. It's always going to be increasing, always going to be decreasing, whatever it is in there. You know, actually, I know what it is. It's always going to be decreasing, right? Because the 0 is bigger than the 1. So I know it's always going to be decreasing. It's always decreasing. From 0 to 1. Okay? There's no changes in directions with that. Now, what if I could say that statement? Well, then this is true, 0.3679 and 1. I'm just plugging those values that I found in. And now what I can say is I can apply that to the integral. So 0.3679 times the interval from 1 to 0. One times the interval. Because that's what that truly means, right? This integral of the interval is basically just multiplying that times 1 by the interval, right? So what I can say here is that since this is 1 minus 0, just 1, 0.3679 is an estimate between 0.3679 and 1 is an estimate for that area. See, I mean, it doesn't give me a very good range there, does it? Like, okay, it's like 0.65 or 0.63 away, right? That's not a very good estimate of that area, but it is an estimate. it does at least give me some idea of what the area is, okay? All right, so use the rest of the class time today to work on your homework, and you will have all of class time tomorrow. So the homework will be due tomorrow night, and I say this tomorrow, meaning Tuesday night. It will be Tuesday night. Okay. All right, see you later, folks.